Welcome to the Rim Break Rodeo. We hope this video helps.
You begin by translating the problem into a quantum-friendly representation. First, decide whether you need an optimization, simulation, sampling, or linear algebra formulation, and pick an encoding like basis or amplitude encoding that preserves structure. Next, allocate the minimal qubit count and layout to match device connectivity. Once done, initialize the hardware, calibrate qubits, tune gates and readout, and prepare the default 0 state. Make sure to test small subcircuits immediately so you detect mapping errors before building larger circuits. You now construct the quantum circuit that implements the encoded algorithm. Choose a circuit ansatz, variational layers for heuristic methods, or structured gates for algorithms, and place entangling gates to exploit quantum parallelism while honoring device connectivity. Insert calibration and error mitigation techniques like randomized compiling or zero-noise extrapolation. Once built, schedule enough measurement shots and randomized circuit instances to gather statistics. Execute batches, monitor hardware metrics in real time, and stream measurement samples to classical storage for immediate post-processing. You finish by measuring the qubits in the chosen bases and aggregating outcome frequencies into empirical probability distributions. Then run classical post-processing to decode bit strings, reconstruct amplitudes or expectation values, and compute the objective or solution metrics. Verify results against small-scale exact solutions or statistical consistency checks, and use those diagnostics to update variational parameters or circuit structure. If results diverge, recalibrate, increase shots, or enable stronger error mitigation. As a troubleshooting tip, rerun failing circuits with randomized compilation.
Thanks for watching. Consider subscribing if we helped you.